It's a great pleasure to introduce the second of John Baez's lectures and his second favourite number, which is 8.
Yeah, they're actually moving up in order of my favor. So my first favorite, my most favorite number will be 24, the last of the talks. So I'm glad to be able to speak to you again. And this time the subject is the marvelous properties of the number 8, which are considerably more tricky to explain than they are for the number 5, which is why it wasn't my first talk. But it's good to start at the beginning with the number 1, namely the one-dimensional line. And so once upon a time, people thought that numbers formed a line, the real line, and that is a very nice and wonderful idea. But as soon as you start trying to solve equations involving real numbers, you get into some interesting difficulties. In particular, in 1545, back when the Italians were having these contests to solve polynomial equations, Cardano published a book that explained the formula for solving a cubic equation. And the interesting thing is that, like the quadratic formula, there's a formula for solving cubic equations that's more complicated, but it has a funny property, namely that it has some square roots in it, and sometimes you get square roots of negative numbers coming into this formula even when the answer to your cubic equation is a real number. So of course for the quadratic equation you've got a square root, and sometimes if you're not careful you may try to take the square root of a negative number, but that only happens when the solutions to your quadratic equation are what we now call complex numbers. And so back in those days, when they didn't believe in square roots of negative numbers, they could just say, well, those are ridiculous cases that don't make any sense. But for the cubic equation, intermediate steps of solving it may force you to take square roots of negative numbers. And Cardano had the guts to go ahead and use this number that he called imaginary, the square root of -1, as a step en route to getting the real answers to his equations. And he was very skeptical about it. I mean, he called it imaginary, and he reassured everybody that it doesn't really exist, but that somehow or other it somehow still does work. And so people caught on to doing that, but they continued to wonder, does this number I really exist? And in fact, that's pretty much what everybody wonders when they first hear about it. A big step towards reassuring people came, well, it's a very complicated history, and I can't really tell you all of it, but one famous step happened in 1806 when a fellow named Argand realized that you can draw the number a plus bi, a complex number, as a point in the plane where you take the horizontal direction to be the real part A and the vertical direction to be the imaginary part B. So now the real and imaginary axes are two axes on the plane. And one thing that does, of course, is it makes the idea of complex numbers a little bit less intimidating. But another great feature is that then different things you do with complex numbers get revealed to be geometrically quite natural things to do. Addition is just adding one arrow with another, so going along one route followed by another. Multiplication's a little bit trickier, but it's very beautiful. So if you want to multiply by the number a plus bi, what you do is you take the plane and you stretch it or squash it a certain amount, and you rotate it a certain amount. So what you do is you take the complex plane, you keep the origin fixed, and you stretch and perhaps rotate the plane so that the number 1 gets sent over to the number a plus bi. Then any other number on the plane will move accordingly, and it will move to a new number, and that's the result of multiplying the one you started with a plus bi. So multiplication just is a matter of operations that are geometrical operations on the plane. In particular, I is just rotating 90 degrees. And so, of course, if you rotate 90 degrees twice, you get back exactly opposite where you were. So that's why I squared is -1. So that sort of demystifies everything. It also makes it clear that every complex number has an inverse. You can divide by any complex number just by undoing the amount of rotation and stretching that you did. So see where 1 goes after you undo that rotation, and that will be the inverse of your number. So that makes the whole business much less scary. But for some reason, it wasn't until a little bit later, in 1835, that William Hamilton realized that what this means is that you can just think of a complex number as being a pair of real numbers, the x and y coordinates a and b of a point on the plane. It's just a pair of real numbers, but that you can say that is the complex number a plus bi. So that sort of completes the demystification process of the complex numbers, if you like. You can just say, don't worry about them. They're just pairs of real numbers. Probably why it took a little while for that to happen. You may wonder why it took 25 years to go from a point on the plane to a pair of real numbers. Is probably people weren't all busy taking classes in coordinate geometry the way that they do now. But what Hamilton then went on and did was to start thinking about what you could do next. And so he was thinking, well, since real numbers were such a wonderful idea in one-dimensional geometry, and complex numbers are so great for two-dimensional geometry, what would be good for three-dimensional geometry, which is actually, of course, the world we live in. So he started trying to invent some new number system, which he called triplets. So they'd be numbers like a plus bi plus cj, which would describe points in three-dimensional space, and they'd be the x, y, and z coordinates of a point in three-dimensional space. And so that launched him on a very interesting quest, which some of you, I'm sure, have heard about. And it built up to a climax. He was sort of really racking his brain in October of 1843. And in a letter that he later sent to one of his sons, he wrote this famous quote: "Every morning in the early part of this month, on my coming down to breakfast, your then little brother William Edwin and yourself used to ask, 'Well, Papa, can you multiply triplets?' Whereto I was always obliged to reply with a sad shake of the head, 'No, I can only add and subtract them.'" So he knew, of course, that he should add them according to the rule of adding one arrow followed by another arrow. In other words, just adding each entry of a triplet with another entry. But the right rule for multiplication eluded him. And we can psychoanalyze what he was trying to do. And I guess, since I haven't read any of his papers during the time of his struggles, I don't really know what he was trying to do. But perhaps, in retrospect, we might guess that what he wanted to do was find what we would call a normed division algebra that was three-dimensional. So what's that? So a normed division algebra, it's a finite-dimensional real vector space. So in this particular case, it would just be three-dimensional real vector space, R3, with a rule for multiplication and a number 1, and also a norm or absolute value that tells you how big any element of A is. And you get an answer between 0 and infinity, not including infinity, such that a whole bunch of familiar rules hold. So we want 1 to act as it should. We want multiplication to be distributive. We want to be able to, since we're in a vector space, you can multiply by any element by a real number, and you want to be able to pull that out of a product in different ways as shown here. You want the triangle inequality to hold for your norm, and you want it to really have the property the only thing whose norm is 0 itself. And finally, the sort of hard part, the tricky part, is to get all that stuff and also have it be that the norm or absolute value of a product is the product of the absolute values. So this is true, of course, for the absolute value of real numbers, and it's also true for the absolute value of complex numbers. So we can imagine that maybe Hamilton was wanting all these good things to be true for his triplets as well. Although he certainly never would have formulated it in this axiomatic language that we're doing now, because that just wasn't available at the time. But there's an unfortunate theorem which says that the only norm division algebras they can only occur if your vector space has dimension 1, 2, 4, or 8. So this is a very wonderful theorem because you have a very general concept, and it turns out there really are just 4 norm division algebras, and one in each of these particular dimensions. So a very general concept seemingly, but really just 4 examples in the end. And 3 isn't on that list, so that's perhaps why he was stuck. But on October 16th, he was walking along with his wife along the Royal Canal in Dublin. He was actually the head of the Irish Royal Society, something like that, the big scientific society. I forget exactly what it's called. He was the president of it, and they were having a meeting that day, and for some reason he was dragging his wife along with him, but it's a very nice canal anyway. And suddenly he had the inspiration that he should seek a 4-dimensional norm division algebra. I'm sure this is the kind of sudden realization that you only get to have after having spent months trying millions of things, so that it's all sort of ready. And he later wrote, he was great at these self-descriptive comments on the history of how he discovered things. He said, "That is to say, I then and there felt the galvanic circuit of thought close, and the sparks which fell from it were the fundamental equations between I, J, and now K, exactly such as I have used them ever since. So I squared is J squared is K squared is equal to IJK is equal to -1. And so he then wrote on this bridge here underneath the equations. So this is Broome Bridge along the canal. I actually went there with some friends of mine, and one of them with a better camera than mine took this nice picture. Now it looks like there's someone lurking there. That isn't Hamilton, though. So we spent a bunch of time looking at the bridge to see if we could see those equations there somewhere, but the bridge is completely covered with graffiti. He wasn't the only one to have some idea while he was walking under that bridge. So there was no way to find the original equations. However, there is a plaque there that proclaims his discovery and the equations. However, ironically, the plaque is covered with graffiti of a non-mathematical nature. So this got him so excited that he actually wound up spending the whole rest of his life working on quaternions, and people have had a lot of arguments about whether that was really good or not for him to do. A lot of people who didn't like quaternions at the time thought that that was the end of him as far as contributing to physics and even certain aspects of mathematics. But they are a wonderful idea. So the idea behind them in modern language is that a quaternion will be A0, some real number, times 1, but I won't write the 1, plus A1 times I, plus A2 times J, plus A3 times K. In modern language, we call this A0 a scalar, a single number, and we'd think of this part as the vector part of A, and indeed we still to this day sometimes use I, J, and K to mean the unit vectors in the x, y, and z direction. The norm, or length, of the quaternion is just the square root of the sums of the squares of the different components, so just like the Pythagorean formula. And he must have been thinking about the equations for quite a while, because his way of writing them was very terse. But if you don't write it out so tersely, the rules for multiplication are as follows. So I, J, and K are all square roots of -1. So you have 3 of them now. And I times J is equal to K. J times K is equal to I. K times I is equal to J. So those are rules that should be familiar to you from the vector cross product. In particular, the quaternions are not commutative. I times J is minus J times I, and so on. And that's, of course, something that was the real shocker, because before that time there weren't really many examples of non-commutative multiplications. There was matrix multiplication, which was non-commutative, but matrices had not really become quite the stuff of everyday mathematics the way they are now, and certainly no one would have thought about calling a matrix a number. So this was the first case where someone said, I've got a kind of number where the multiplication doesn't commute. So what's really going on is that we're combining scalars and vectors, and the multiplication combines all the things that we learn about different ways to multiply things. So the scalar part of a product would be the product of the scalar parts minus the dot product of the vector parts. This funny minus sign because of the -1 there. And then you'd have the scalar times the vector. So I guess people call this scalar multiplication, the other order, and then the cross product. So all the 4 different ways we multiply scalars and vectors today are packed into a single formula. But it's very important, if you're trying to understand the history of this, to realize that nobody had ever thought about the dot product or the cross product at this time. It was actually much later. In fact, the first person to get their math PhD in the United States was Josiah Gibbs, the chemist / mathematician, and Gibbs broke the quaternion into its scalar and vector part and began treating them separately and wrote a textbook about it in 1901, which introduced the dot product and cross product notation. But between 1835 and 1901, it was really quaternions that did the jobs that we now do with vectors. And so there are lots of textbooks on quaternions. And in fact, in the day of when Gibbs was getting his PhD, there were some universities in the United States where the only graduate mathematics course would be about quaternions. So quaternions were quite a thing then. Then when Gibbs invented his vector approach, a big battle started between the quaternionists and the vector people. And I guess you can guess who won if you've ever taken a math class. You never hear about quaternions, or hardly ever. You hear about vectors a lot. And so apparently, in many applications, it was just more useful to break things up into the 2 pieces. And that's really just the beginning of the story, because then later some physicists invented things called Pauli matrices, which are essentially quaternions in disguise, but in the disguise of 2x2 complex matrices. So quaternions are actually important still, but they're often not called that. But anyway, that's not my story. That's about the number 4, and that would be a whole other story. My story is really about the number 8. So the very day after this walk, Hamilton sent a letter to his old college pal, John Graves. Actually, John Graves was the guy who got Hamilton interested in algebra in the first place. He was also a math major, I guess a math undergraduate with Hamilton, but he'd gone on to become a lawyer and was just sort of doing math as a kind of hobby, but corresponding with Hamilton. And Hamilton sent his friend an 8-page long letter describing the quaternions. And on October 26th, Graves sent the letter back, and he was very impressed, but also sort of puzzled. And it's interesting to hear how he was sort of puzzled. So he said, "There's still something in this system of yours which gravels me. I have not yet any clear views as to the extent to which we are at liberty arbitrarily to create imaginaries and endow them with supernatural properties." So the whole idea, you see, of writing down an algebraic system where you just like get to make up the rules however you want was not at all this kind of thing that was done then. And so it was, even though in some sense Hamilton had, it was because Hamilton himself had realized that the complex numbers could be thought of as just pairs of real numbers, that he had been empowered to go around making up other number systems. But most people didn't think that that was something you could just do. And so Graves asked, if with your alchemy you can make 3 pounds of gold, that is I, J, and K, why should you stop there? And indeed, Graves didn't stop. So Graves wasn't too shy, because he began working on this idea himself. And in fact, on the day after Christmas, which shows you how sociable this fellow must have been, Graves sent Hamilton a letter about an 8-dimensional norm division algebra that he had invented, which he called the octaves, which I now prefer to call, and many people prefer to call, the octonions. And in January 1844, he sent Hamilton 3 more letters about these octaves. And it's very interesting that he tried to construct a 16-dimensional norm division algebra, because in fact there is a certain way to construct these algebras where each time you do a systematic process that doubles the dimension. And that's usually attributed to Cayley, but obviously Graves had some inkling of that. So he tried to construct a 16-dimensional norm division algebra, but he met with an unexpected hitch and came to doubt that it was possible. In fact, there is a very interesting 16-dimensional algebra that you can get by applying this procedure to the octonions, but it's not a norm division algebra anymore. It doesn't have those properties that I listed. So the quaternions, as I mentioned, are non-commutative, and in June, Hamilton, who probably wasn't paying that much attention to these letters, finally noticed that the octonions are non-associative, and it's in fact in this discussion of the octonions that the word associative was first invented, or first used in this mathematical way, to mean that it matters how you parenthesize a product. So the quaternions are at least associative. Non-associative algebras still labor under a lot of prejudice. That people tend to regard that as like beyond the pale as far as algebras go. Of course, there are other kinds of things like Lie algebras that aren't associative but satisfy some other kind of laws. But just an algebra that doesn't have any associative law, we tend to, I know I tend, when I first started studying the subject, to think of it as like something too bizarre to be worth studying. And so the octonions have always remained a little bit obscure, well, I should say incredibly obscure, compared to, say, the quaternions or various other algebras. There's a very nice book by a guy named Schaefer on non-associative algebra, and if you've ever studied associative algebras, you'll be shocked to see like how many of your favorite theorems are still true for non-associative algebras. They're not nearly as bad as you might think. So Hamilton offered to publicize Graves' work, being the head of the Irish Royal Society, or whatever it's called. I'm sorry, I'm forgetting the name of it. He was in the position to do that because this was in the day when papers to the main journal were read out loud at meetings of the society and then recorded later on afterwards. But Hamilton never got around it because he was so obsessed with the quaternions. And that was sort of unfortunate for Graves, because then Cayley, the young mathematician Arthur Cayley, rediscovered the octonions in 1845 and did publish them and got credit for them. In fact, as soon as that happened, Graves published an article in the same magazine saying, I really discovered them first, and Hamilton wrote a letter saying, yeah, he really did discover them first. But they became called Cayley numbers for a while. This paper by Cayley is sort of obscure too, because in fact this paper was so full of mistakes that it has been left out of his collected works. But the point is the octonions were only included as an appendix to this paper, which had nothing to do with the main topic of the paper. People were a little more relaxed about math papers in those days. There would be lots of mathematicians who just like, work. After I get 30 pages, I staple it together and call it a paper. And so this paper was about elliptic functions, actually, which is something quite unrelated. And for some reason, he just stuck it in the appendix saying, hey, and I discovered this 8-dimensional number system. So if you look in the collected works of Cayley, you'll see only the appendix appears. The rest was, in fact, completely wrong. So these things probably helped contribute to the octonions' sort of lack of recognition, this sort of cloud under which they arose. But let me tell you what they are and why they are actually incredibly interesting. So here's how you could remember how to multiply quaternions, and then I'll tell you how to multiply octonions. You just need to remember a few things. You need to remember that 1 times anything is that same anything. That's easy to do. You need to remember that I, j, and k, these 3 guys, they're all square roots of -1. And then you just need to know how to multiply 2 different ones. Well, of course, if you know the vector cross product, that's easy because it's just the same. But it can be nice to sort of draw it as a little chart here. And the idea is that there's an orientation to this circle, and if you go with the orientation, then it works very nicely. I times j is k, j times k is I, and so on. But if you go against the circle, you get a minus sign. So j times I is minus k, and so on. So that's easy to remember, I hope. And so the octonions are the same way, except that the picture is a little fancier. So it's like this. So you've got 1 acts like 1 should. Now you've got 7 square roots of minus 1, and you have to remember this picture. Now, I'll tell you, it's not so hard to remember this picture. The first thing to realize is you don't need to remember the names of these things, okay? Those are just arbitrary names. In fact, I probably would have liked to name them after the 7 dwarves in the Disney movie and call them Sleepy and Grumpy and things like that. But so that would work just as well. The particular numbering system here that I've chosen has a certain nice property, but it's really not essential. So you shouldn't think of that as like extra work. So you should mainly realize that this is an interesting picture that has 7 points, these blobs. It also has 7 lines. 6 of them really look like lines. 1 of them looks like a circle, but I will call it a line. And what's nice about it is that each point lies on 3 different lines, and also each line has 3 different points on it. So in fact, there's a complete symmetry between points and lines in this setup. That is, if I switched what I called points and what I called lines, it would still be abstractly the same setup. The hard part to remember, which isn't all that hard, but you do have to remember it, is the correct orientation of these arrows, because the way it works is that if you go around with the flow, it works just like the quaternions did. So for example, E5 times E2 would be E3. And you have to imagine that all these lines really loop around. So in fact, this circular one is sort of the best one. So E2 times E3 would be E5, and then E3 times E5 is E2. But if you go against the flow, you get a minus sign. So for example, E2 times E7 would be minus E6. And so to remember it, you basically just need to remember that these arrows should basically just go around clockwise, or if you prefer, make them all go around counterclockwise. And all these arrows should sort of go in from the apex to the base. Although I think if you switch them around so that they all went from the base to the apex, that would be fine too. So just draw something that looks pretty nice and symmetrical, and you're pretty likely to get the right thing. I think, in fact, you are. But I'll just mention the reason for this goofy-looking numbering system is that what's nice about it is that this picture has a clear symmetry under rotation by 1/3 of a turn, and the numbering system has been chosen so that when you turn things 1/3 of a turn, the index doubles mod 7. So 1 doubled gives you 2, 2 doubled gives you 4, 4 doubled gives you 8, but that's the same as 1 mod 7. 7 mod 7 is 0, so it doesn't change at all when you rotate, so it's got to be in the middle, and then these other ones also have this index doubling thing. So if you're ever trapped on a desert island and need to do lots of octonion computations to keep from going crazy, it's good to use this particular numbering system, because then you know that you can just double all the indices on any formula and it will still be true. But that's just sort of for fun. That's not necessary. Not necessary to remember those numbers to remember the idea. Actually, those 7 points really are part of 8 points. Namely, I hadn't drawn the multiplicative identity of the octonions, and so if you draw that in there as well, we get a cube. So this cube, if I squashed it down and left out the 1, we'd be back down to here. But if I sort of pull that E7 out to the corner and to the front, it will look like this cube here. And then, so what this is really is a picture of Z mod 2 cubed. So there's a field with 2 elements, and this is the 3-dimensional vector space over that field. And the things that I had been calling lines before are really planes through the origin. So for example, there'd be a plane here. This one really looks a lot like a plane, and that would correspond to the line that had E3, E4, and E6 on it in the previous transparency, and similarly. So what, this is a little bit of a digression, but what we're really doing is we're doing projective plane geometry over the field with two elements. This Fano plane is the projective plane over the field with two elements. So the fact that 2 cubed is 8 is really what's at work here. So you can then sweat and suffer and check just from this picture that you really will get a normed division algebra. So if I have an octonion, it will be some number times 1 plus some number times E1 plus some number times E2 and so on, where those numbers are all real numbers. Then the norm of it will just be the square root of the sum of the squares of all 8 of those numbers, all those coefficients. So the norm is just sort of the obvious thing. And then what you have to really suffer to check is that the norm of the product of two things is the product of the norms. And I've done it. It's true. And you can do it too. So that's all fine and dandy, but it's bound to leave you quite mystified as to what's really going on there. I'd like to give you a more high-level explanation, but this will, in fact, I will leave out a lot of details. I actually have a web page on the octonions where I fill in all the details of what I'm about to say, but I think I don't think you want to hear all that now. But it's sort of an interesting outlook on what's going on. So last time I told you a little bit about spinors. So there's this funny idea that there are, in addition to things called vectors, which when you turn them around 360 degrees come back to exactly where they were, there are these other mathematical entities. They also form an abstract vector space, but they have the property that it's not really the rotations that act on them, but something called the double cover of the rotation group. And what that winds up meaning is that if you rotate a spinor by 360 degrees, it doesn't come back to being where it was. It actually comes back to being opposite where it was. But then if you rotate it around 360 degrees twice, it does come back to where it was. That is, the rotation group has a representation or a way of acting on these spinors as well as vectors. But I lied slightly. It's not really the rotation group, but this double cover. So there are two things in this double cover for each thing in the rotation group. So there's a distinction now between not doing anything and a 360-degree rotation. That's a mathematical possibility. And the exciting thing to me is that it's realized in nature that a lot of the important particles in nature are described by spinors, that when you actually grab a hold of them with a magnetic field or something and you turn them around, they don't get back to where they were. And protons and neutrons and electrons are among those particles that are called spinors. A typical example of a particle that is described by a vector is a photon, the carrier of light. Now it turns out that mathematically there's a way to multiply a spinor and a vector and get a new spinor. So there's an operation that takes a spinor and a vector and produces a new spinor. And that mathematical operation is used throughout physics to describe how particles interact. In particular, if you grab a book on quantum field theory, you'll be likely to see somewhere a picture that looks like this, which is used in many ways, but one way, the first way it was used, is to describe the possibility that you can have an electron moving along, and that's a kind of spinor, and it absorbs a photon, a particle of light, and then it gets deflected, and then it keeps moving along. So the electron keeps moving along. When you try to describe that operation, or that process, the process of an electron absorbing a photon, it turns out that mathematically you need to use this operation of taking a spinor and a vector and multiplying it to get a new vector. So that's a very fundamental thing in physics, but there's something very interesting that happens. This stuff I'm talking about here is very general, and it would work in no matter what the dimension of physical space was. So there, as you know, there are people like string theorists who think that space-time has 10 dimensions, and mathematically all those are perfectly permissible options, but there's certain cases where the space of vectors happens to have the same dimension as the space of spinors, and then this multiplication actually gives you a normed division algebra. You can say the spinors are, quote, the same as the vectors. They're not the same, but they're the same dimension, and you can get a multiplication. And so you can look at different dimensions of space, and if you're a physicist, I'll emphasize that I'm talking here about Euclidean space, not Minkowski space-time here. And in different dimensions of space, well, the vectors just have that very same dimension. So you probably think we're here in three-dimensional space. Our vectors are lists of three numbers, but you can imagine these other options. And then you can work out what the dimension is of spinors in each of these cases. And you see they follow a rather peculiar pattern that goes, I should have maybe written R1, 2, 4, 4, 4, 8, 8. And there are certain cases where the dimensions match. So in dimension 1 they match, and then you get a normed division algebra, which in this case is real numbers. So in this case, the operation of multiplying a vector and a spinor just is ordinary multiplication of real numbers. In 2 dimensions, they match, and you get the complex numbers. In other words, you can think of vectors in 2 dimensions as being a single complex number. You can also think of a spinor in 2 dimensions as a single complex number, and this operation, this multiplication operation, is just complex multiplication. In 3 dimensions, they don't match, so that's why Hamilton was suffering in October. In 4 dimensions, they do, and you get the quaternions, and then no, 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 but then in 8 dimensions, yes, you do again. And those are the only dimensions where they match, because there's a beautiful fact that's very related to the octonions and related to the magical features of the number 8, which is that this chart that I wrote down, I quit at the number 8. And the reason why I quit at the number 8 is because, in some sense, it repeats after 8. So you might wonder, like, what about 9 or so on? But it turns out there's a formula called Bod periodicity, which says that spinors in 8 dimensions more than some dimension you're studying have dimensions 16 times as big. So when we get up to dimension 9, which is 8 more than 1, this row that I didn't fill in here, so here you'd have R9, we'd get spinors that were 16 times as big. So we'd get R to the 1 times 16. So you get R to the 16 would be the space of spinors in 9-dimensional space. And you'll notice that 16 is a lot bigger than 9. And so the point is that ever after that, the spinors are bigger in dimension than the vectors. And the vectors just never catch up. And so these are the only options you have for the normed division algebras. And that's sort of how it works. And I fill in all the details of that proof in on my webpage. So now this more recently has had actual applications to physics, or at least to the theory of superstrings, which is a untested but very popular theory of physics. And I don't actually believe in superstring theory, but it's so beautiful that I can't resist studying it. And it has some amazing features to it that for some reason string theorists don't talk about enough, that at least I find to be something that's sort of attractive about it in a very theoretical sort of way. So in string theory, instead of particles being little dots, they are little loops of string, or they might be little open-ended strings, but let's just talk about closed strings. And they can vibrate in different ways, and different vibrational modes, different kind of ways that they can wiggle, will correspond to different particles. And you can imagine a string moving along with a passage of time. Well, time is some dimension that I can't really point at, but so I'll just say it's up here. So here's my string now, and then as time passes, it's moving along forwards in time. And so it will trace out a 2-dimensional surface. I'm drawing it to look like a cylinder, although it could be much more wiggly. Traces out a surface. And if you just look at a little piece of that surface, it's a 2-dimensional surface, you could imagine studying how the string wiggles by seeing how it's wiggling, how that surface moves. Or in other words, you can imagine that You have a fixed surface, and then you can say, well, if I give the string a little kick, it might move a little bit at right angles to that surface. So since the surface is two-dimensional, then if there are n other directions the string can go, that could only happen if the total dimension of space-time was n plus 2. So I guess in my picture here, we've got 3 dimensions total. The surface is two-dimensional, and that means there's just one direction at right angles to the string. So that would be a picture of n equals 1. Now it turns out that supersymmetric string theories, that is, string theories that combine spinors and vectors on an equal footing, which is part of the thing that really makes string theory work and be attractive, those are only possible when the space of the dimension of, when the space of vectors, the vectors at right angles to the string, namely n, that dimension, matches the dimension of the space of spinors. And as I just sketched, that there are only 4 options for that, which is n is 1, 2, 4, or 8. And that number plus 2 is the dimension of space-time. So it's when space-time has dimensions 3, 4, 6, or 10 that we could set up a theory of superstrings. And so those correspond to the reals, complexes, quaternions, and octonions. In other words, the directions perpendicular to the string surface could be thought of as reals, complexes, quaternions, and octonions in those 4 cases. Now the really amazing thing is that when you're studying classical mechanics, when you're not trying to get quantum mechanics into the game, all 4 of those superstring theories are mathematically consistent. But when you take quantum mechanics into account, only one of them is mathematically consistent, and it's the most complicated one. It's the n equals 8 one, and that's why string theorists will sometimes tell you that string theory only works in 10 dimensions. Sometimes they'll only tell you it works in 11 dimensions, but that's something else. I'm not going to talk about that today. So they keep discovering new stuff. That's actually called M theory. That's some other theory where it involves some kind of 3-dimensional surfaces instead of 2-dimensional surfaces. So you get one extra for free or something like that. But the amazing thing is that if all this superstring theory stuff is right, and space-time really is 10-dimensional, then all the vibrations of the strings that we see manifested as different kinds of forces and particles, like the electrons and photons and so on, they would all really be described by octonions. So in that case, it would really be not Hamilton, but his friend Graves, who has to be considered the really insightful, foresightful one. So I don't know if that's true, but anyway, we're sort of waiting to see if string theory gets some experimental confirmation. Now let me switch subjects, seemingly. Let me talk about packing pennies on the plane. There are 2 maximally symmetrical ways to put pennies in a lattice. By a lattice, I mean a pattern that repeats in 2 different directions, repeats periodically in 2 different directions. So one obvious lattice is this square lattice. It's called z squared because z means the integers, because the Germans were in charge back then, and z stands for Zahlen, which means number. And so the point is that the centers of these spheres, you could describe them by pairs of real numbers, but not just any old pairs of real numbers, but pairs of integers. So that's one way you can pack pennies. But if you've ever played around with it, you'll know that's not the most efficient way to cram a bunch of pennies into a small area. The most efficient way uses instead a hexagonal lattice like this, where each penny touches 6 others. It actually turns out that that's the densest possible way to pack spheres in 2 dimensions, is doing it this way and just going on forever. I've just drawn a small portion, but you should imagine it goes on forever. Proving that is actually pretty darn hard, although it seems obvious. And this lattice here is called A2 for no particularly good reason. The 2 means it's in 2 dimensions. The A doesn't really mean anything in particular. Now, one nice thing about them is that you can think of the centers of those pennies as certain complex numbers, because Hamilton's idea was that a point in the plane, you can think of it as a complex number. So if we use the lattice Z2, then what we're getting are complex numbers where the coordinates are integers, like these ones that I've drawn here. And one nice thing about them is that they're closed under addition. Well, that's pretty obvious. That's just because it's a lattice. But they're also closed under multiplication. So like I times I is over here. It's -1. So we'd say it's like a sub-ring of the complex numbers. And the same thing is true of this hexagonal lattice. Those are sometimes called the Eisenstein integers. Eisenstein was a student of Gauss, and one of the things he was forced to do is to study these. And here, what the idea is that this number here is actually a cube root of 1. So, well, this is actually a 6th root of 1, but it's also omega plus 1 as well. And so these two are going to be closed under addition and multiplication, basically because, well, when you multiply omega by itself twice, you get over here, this is omega squared, and when you multiply it with itself 3 times, you're back here to 1. So every integer linear combination of 1 and omega is in this lattice here, and they're closed under addition and multiplication. So there's something nice here about this problem that started out being a problem of beautiful symmetrical ways to pack pennies, winds up getting related to the complex numbers. And there's a lot more to say about that. It sort of shows up, these things show up in number theory. But we could say, okay, let's go up a dimension. Well, in 3 dimensions, of course, you could pack spheres in a cubical lattice, put them at, imagine that like you had space full of cubes and just stuff a sphere in each cube. But there's a more efficient way to pack spheres, as you can notice by going to the grocery store and looking at the oranges or something. They're always packed in this type of way. This is called an A3 lattice. So each slice of it is an A2 lattice, and then you put a new layer on top of the old layer, sort of in the sort of obvious place, the place where the orange will be able to go down as far as possible. And that turns out to be the densest possible way to pack things in 3 dimensions. And that actually is really hard to prove. It was proved by a fellow named Hales only fairly recently, like 1992 or something. I forget. But that was incredibly hard to prove. In fact, at first, the journal that he was going to try to publish the proof in was going to publish it, but with a note saying the referees were too tired to check the proof. And he just didn't like, Hales wouldn't stand for that, and I guess he made them. He made them check the proof. Or maybe they just pretended to check the proof. But in fact, they're now attempting a computer-verified proof. It basically just uses a lot of spherical trigonometry in a very clever way that goes on for hundreds of pages. So now you can imagine, what about higher dimensions? For example, 4 dimensions or 8 dimensions. Well, it turns out you can define a kind of z to the n lattice in any dimension, and you can pack spheres that way, but the density, that is the percentage of space that's filled by spheres, will drop and drop. And there's also a way to generalize the an lattices to higher dimensions. I won't really describe to you exactly how it works, but it's some kind of systematic process generalizing what we've done so far. And they're denser, but their densities drop as well. However, in 4 dimensions, something interesting happens. In 4 dimensions, it turns out that there's a way to pack spheres that's better than either of these. And here's how it goes. So the interesting thing about 4 dimensions is that if you take this cubical lattice, or hypercubical lattice, Z4, by the time you get to 4 dimensions, there's enough spaces between the spheres that you can actually stick more spheres in the holes there. It seems paradoxical at first that there'd be that much room that way, but it's really just a consequence of the Pythagorean formula in higher dimensions, as I'll show you. And so it turns out that in 4 dimensions, you can take your Z4 lattice and slip a whole nother copy of the lattice in between the spaces of the ones you've got. And so you can get twice as many spheres in there. And the reason why is this. So your Z4 lattice had spheres centered at these places where these coordinates were integers, and each one of these centers will be distance 1 away from its nearest neighbors, because you could add 1 to any of these integers and get a new sphere whose center is 1 away. And now what we're going to do is we're going to pack a whole bunch more spheres centered at these points where these n1, n2, n3, n4 are integers, but we're adding a half to them to make them as far away as possible from the ones we've got already. And if you look you'll see that the centers of these new spheres are just as far away, namely distance 1, away from the old spheres as the old spheres were from each other. Why? Well, just look at the distance between the point 1/2, 1/2, 1/2, 1/2, and the point 0, 0, 0, 0. The distance between them by the 4D version of the Pythagorean formula is that. But a half squared is a quarter. And we're adding up 4 quarters, so we get 1. So that's what's special about 4. It's just then that it kicks in. It's actually quite hard to visualize packings of spheres in higher dimensions, not just because they're higher dimensional, but because they do things that are so drastically different than what you'd expect from a few low-dimensional examples. So this is how far away those centers were when we were in 4 dimensions. But if you imagine we were in like 1 trillion dimensions, then there'd be like points that would be way, way, way far away from the centers of the spheres that you already had. So you could if you're like in trillion-dimensional space, you could pack space with little ball bearings in a cubical array, and there'd be like there'd be places in between there that would be like miles from any one of those little ball bearings. So that's why this kind of funny stuff can happen. So this is called the D4 lattice, this sort of double dense version of the hypercubical lattice, and it turns out that it is the densest possible lattice in 4 dimensions. No one knows if it's the densest possible way to pack spheres, but it's the densest possible way, it probably is, but it's been shown to be the densest possible lattice, that is, periodic way of packing spheres in 4 dimensions. And the really nice thing is that points in this lattice, you can also think of them as quaternions, because you can think of the coordinates as A, B, C, and D as giving you a quaternion. So those coordinates are either all integers or all integers plus a half. And just like we had in the other cases, they're closed under addition and also multiplication. So you can check sometime. If I multiply 2 things like this, I get another thing like this. And so it's a really beautiful thing that's special to 4 dimensions. And they're called the Hurwitz integers. Each one of them has 24 nearest neighbors, as I'll show you in a second. So that means that when we pack these spheres this way, each one will be touching 24 others. When you pack 3-dimensional spheres, the best you can do is get each one to touch 12 others. But in 4 dimensions, each one can touch 24 others. And here's what it looks like. So now, as I said, it's a little hard to draw in 4 dimensions, but if you think about it, it's already hard to draw in 3-dimensional things on the plane, because you're already having to cram a 3rd dimension onto the plane. So if you didn't stop at 3, why should you stop at 4? So we will have these coordinate axes, the I direction, the J direction, the K direction. That's like normal perspective. And then we've got a 4th direction, the 1 direction. I'll just stick it over here. It's no worse than what we were doing before. Well, maybe 4/3 is bad, but it's not qualitatively worse. And so some of our Hurwitz integers will just be plus or minus 1, plus or minus I, plus or minus j, and plus or minus k. Those will all be distance 1 from the origin, and so they'll be centered at these points here. This thing here is a picture of a certain solid in 4 dimensions, which is the 4-dimensional analog of an octahedron. It's called a cross polytope. It's a very regular solid in 4 dimensions. But then we also have 16 more, namely the ones where the coordinates are all multiples of a half. So we have 2 times 2 times 2 times 2 equals 16 choices of these, which I've drawn here. And these are the corners of a hypercube. A cube in 4 dimensions will have 16 corners. So that's 8 of one kind, 16 of the other, for a total of 24, which looks like this. So this is a picture of the centers of the spheres nearest to the origin in this D4 lattice. It's a very nice thing to look at, because you can see, if you turn your head, you see a large square here. It's a very symmetrical, interesting pattern. Of course, it's just a 2-dimensional shadow of a 4-dimensional pattern that's really, really symmetrical. And so those are certain unit quaternions, and because they're closed under multiplication, and because the length of a product is the product of the lengths, and these are all the quaternions of length 1, it means that if I multiply any of these 2 guys, I'll get another one of these guys. So it also forms a group. So that's the D4 lattice. And then the dimensions, you can keep on copying tricks like that. The dimensions go down. So these are how it works up to dimension 8. But then in dimension 8, there's another surprise. Namely, at that point, there's enough room between the spheres in the D8 lattice that you can slip a whole other copy of that lattice into the cracks. And then you get this lattice, it's really nice, called the E8 lattice. And those are certain special octonions called the Cayley integers. And they're closed under addition and multiplication as before, as we've seen before. And now it's so high dimensional, it's much harder to visualize, but each one has 240 nearest neighbors. And if you look at my webpage, you can see the coordinates for them. They're a nice pattern. It's not as bad as it sounds. So each sphere in there would touch 240 others, and it's been proved that that's the densest lattice packing, and it's also been proved that that's the most number of spheres you can get to touch a single sphere of the same size in 8 dimensions. There's no wiggle room, actually. You can't even wiggle them at all. They're sort of locked in place. And it looks like this. So now we're getting really desperate. We're projecting an 8-dimensional shape down to 2 dimensions. So it's only a rough indication of what's going on. But if you had a lot of time, I've never even done it, you could count that there would be 240 dots here. And then I guess they're connecting each dot to its nearest neighbors with edges. This pattern showed up in the news because recently people have been doing some interesting calculations involving E8 and also coming up with some theories of physics involving E8. And if a news reporter asks me, show me a flashy picture of an E8, well, it's a little hard to oblige them because it's 8-dimensional, but you just get this off of somebody's web page. John Stembridge worked this out. There's a lot to say about this thing, but I won't, I guess. So in fact, I should probably stop here, but I will say one thing that indicates where this goes from here, which is that all these different lattices that I've been talking about, they're a lot more than just fun ways of packing oranges if you're living in 8 dimensions. There are a lot more to them than that. They all give rise to certain symmetry groups, groups of continuously adjustable symmetries called Lie groups, and they're very nice ones of a type called semi-simple Lie groups. And when Cartan classified the semi-simple Lie groups, or let's say simple Lie groups, near the beginning of the last century, he found that there are a whole bunch that were groups that people knew about, like rotations in different dimensions and stuff like that. And there were 5 extra ones that he'd never thought about before that just sort of showed up in the process of classification. And the biggest, baddest one of all was the one that he called E8. And E8 is a very strange thing because no one really knows what it's the symmetries of. It's a beautiful symmetry group, but no one knows anything simpler than it that it's the symmetry group of. It's the symmetry group of itself, and that's in fact sort of, in some ways, that's the simplest description of what it's the symmetries of, but that's not very helpful if you're trying to get an understanding of it. It shows up as symmetries in string theory, and I suspect that must be because this E8 is related to the octonions. The 8, of course, is a dead giveaway, but it's really related to the octonions in a lot of ways. But curiously, the people who are working on string theory, that's not how they see that E8 shows up. They just see that it has some property that they like. So I think that's a good place to stop. It's where things start getting really mysterious. Thanks.